Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the physics series we will be looking at oscillations. Okay, so oscillations, well, I think it's like the fact that I start so energetically then I end up just blanking out. Okay, never mind. Let's just start. Okay, so what is an oscillation? You put a pendulum, you put it to one side, it'll oscillate, right? It moves in a repetitive motion to the right and to the left or something like that. And likewise, there are many things that oscillate. Basically, it just moves from one side to the other repeatedly and repeatedly. So that is what oscillation, like that's what you mean by oscillations in a sense. And yeah, I guess that's the first point. Simple examples of free oscillations. Yeah, your pendulum oscillating freely, or I don't know. I can't think of anything else. Or if you put like something on a spring or something, and like you put a mass underneath a spring and you hold it there first, then once you release it, it will start oscillating up and down, up and down. And yeah, things like that. Like I think you know what oscillations are, so that's not that hard to do. Okay, so let's see. The next one is investigate the motion of an oscillator using experimental and graphical methods. Why? Okay, this just sounds more like practical than actual theory stuff, so never mind. So in practical, I think you usually have that pendulum experiment in all its weird forms. So yeah, that's so how do you investigate that experimentally? You timing each oscillation. Of course, you don't time one single oscillation because one oscillation will be quite fast for the human, in terms relative to the human reaction time of 0.2 seconds. So instead, you take about 20 oscillations, which is a decent amount of time. Usually for a pendulum, it's quite a bit of time. And then after you get 20 oscillations, you divide it by 20, and you take a few trial runs of it, and you get the time of one oscillation. And then you can graph those values. Maybe you've changed the length of the string, and then you see what's the effect of the length of the string over the oscillation and things like that. So that's how you investigate the motion of something that's oscillating. If you have oscillator, it may be something that just keeps moving from left to right or something. Yeah, similar logic. I think you get it. Okay. So the next point, okay, basically the terms amplitude, period, frequency, angular frequency, and phase difference. Okay, great. So amplitude, well, I think you all know what this means. It's just the height of the curve, like the magnitude of how high the curve goes. If you imagine like a sine curve, the amplitude would be, if it's just sine x, like say you have the equation y equals sine x, the amplitude is 1 because that's the maximum point. So from 0 to 1, you get the amplitude of 1. And likewise for your experimental results or anything that you get, you can use, okay, maybe not the experiment results, but more of just monitoring where it moves from point to point. Like if your pendulum is moving from the center onto the left, what's the maximum distance that it travels? That's the amplitude. Then the period would be the time that it takes to complete one oscillation, which is usually represented by a capital T. So frequency is the 1 over the period because it just tells how many oscillations it finishes within 1 second, and or like 1 minute or something based on your units. If you're using second, it will be hertz, so yeah. Angular frequency will be the angle that it travels within 1 second. Like, not really angular, but okay, you think about it in terms of an angle. So how do you relate this to angles actually? Even if the motion looks linear, you can imagine it as, let's say a ball is moving in a circle from the topmost point of the circle. That will be like the center point of the pendulum, right? Then as the pendulum moves to the right, the ball is also moving in a clockwise direction until a 90-degree mark. So when the pendulum is at the rightmost amplitude, the ball will have completed 90 degrees. When the ball moves down to the bottom until it completes 180 degrees, the pendulum will be back at the center, and then as the ball moves back to goes to the left to complete 270 degrees, the pendulum will be at the leftmost amplitude, and then as the ball reaches back to the top, the pendulum will move back to the center. That's 360 degrees. So that's what you mean by angular frequency. Right, so yeah. And then phase difference. Phase difference, in order to visualize phase difference, you draw it out in the sinusoidal curve, and then you see how what's the difference between this particular oscillation and that particular oscillation. What's the difference between the two of them? Yeah, so like if they are displaced, like imagine translating the curve by this many degrees or something, that will be like the phase difference in a sense. Yeah. So I think you understand how it works, okay? Alright, so the period in terms of frequency is, well, 1 over frequency, because yeah, they're just 1 over each other lah. But if you're trying to use angular frequency to get the period, angular frequency, as we learned last time, would probably be like W here. Okay, not last time, this is slightly different. So this is W. It's that W thing, I don't know what to call it. So that value isn't equals, you can't just 1 over the value and get period, right? So how do you get from angular frequency to period? You first have to understand what's the difference between the angular frequency and the frequency, right? Which I think you've gotten from what I described to you just now. So the angle is, well, it's something that, you know, the maximum that you can get is 2 pi, right? So if you times the angular frequency by, I mean, if you think about it, the amount of time it takes to complete one oscillation, that will be equivalent to getting the angle of 2 pi, right? So how do you get angular frequency? Well, you can just represent it with 2 pi times t. So yeah. So W will be like 2 pi t. Yeah, that's pretty much it. There's nothing else to say. Okay, never mind. That was weird. Never mind. Wait, is it 2 pi over t? I think so. Never mind. So how do you get to the equation of... Okay, so now I think it'll be more clear when we go through the subsequent points. So now we go to the very important equation of acceleration equals to negative w squared x. So what does this mean? Well, if you were to write this down into an actual worded definition, you would say the defining equation of... Okay, so simple harmonic motion is a constant oscillation of an object in which the acceleration of the object is directly proportional to the amplitude of the object and acts opposite to the direction of its motion. Yeah, that's pretty much it. So negative represents the opposite direction of the acceleration, and the proportionality is, I think, is pretty obvious because w squared is always constant. Yeah. Oh yeah, so w is actually 2 pi over t. I'm so sorry. 2 pi over t. Right, so how do you get this equation? Well, you first start with what the original... You start with displacement, right, first of all. So x is displacement. So how do you get the displacement of that particular pendulum or whatever that is oscillating? You would first represent it with a sinusoidal equation, because you know that it increases and then it decreases. Like if you imagine the right as positive and left as negative, you get a positive and a negative value. And you realize that you cannot just put sine x, right? Because it doesn't, sorry, or sine t, because it doesn't, you cannot always expect the magnitude of the amplitude to be 1. So you put in the amplitude in front, which will be represented by x0. And then after that, you need to figure out what exactly makes the x increase and decrease. So as you can see, it's the time that does it, right? But time doesn't correlate to angles. So how do you make the time into an angle? You use angular frequency. So you time the angular frequency by the time, which would be equals to 2 pi over t, 2 pi over period times time, which would give you a fraction of 2 pi. That will be an angle, right? So that's how you get your equation. X equals to x naught sine w or angular frequency or times t. And that is actually the starting equation that you get. I mean, you can use cosine or negative sine or whatever, but because you eventually will get the same conclusion of an acceleration equals to negative angular frequency squared times x. I'll tell you how, but I think this is the easiest way to get it from some sine. So now you just differentiate it, because you know how to get speed, you need to differentiate displacement to get speed, right? So let's differentiate this once. You will get x naught w cosine wt. Yeah. So if you differentiate sine, you get cosine, right? So now you have x times w, because w is a constant, you can just bring it in front, and then cosine wt. So let's differentiate this again to get acceleration. Yeah. But before we differentiate it again, let's look at it in and see how it correlates to the equations that we have provided about v itself. So x naught w is kind of like the speed as well, the velocity on its own, because if you think about it, wait, no, not really the velocity, but you get the idea. Because the angular frequency is kind of like a speed of its own, right? Like if you think about it in a way, it's like something over t. So when you time the displacement by that, you'll be getting some kind of angular velocity, and that's why you can use, if you put x amplitude x naught on it, you realize that that's when you get the maximum velocity or the amplitude of velocity. That's what you represent with v naught. That's why the equation for v is equals to v naught cosine wt. Okay, and if you want to represent it in a different way, if you realize that cosine is and sine are always related in some way or the other, and if you look at the original form, the x naught w cosine wt, w square root of x naught squared minus x squared. I'll write it down, I hope, and I think that will make it clear to you. Yeah. So now let's move on to acceleration. So as we differentiate x naught w cosine wt to get acceleration. So what does that give us? That will give us negative x naught w squared sine wt. Yeah. Great. So what does that mean? Well, we can then relate it back to what x is equals to, right? That is x equals to x naught sine wt, and your acceleration is equals to x naught w squared sine wt times a negative sign in front. So the only difference between the acceleration and the x itself is the negative w squared, and from there you can get the equation acceleration is equals to negative w squared times x. Yay, we did it. I took way too much time for that. Okay. Now let's move on. So you can actually draw all of these out in actual sine graphs, or like sinusoidal graph, like sine, cosine, whatever. And if you start with something that's not a sine graph, you can still get the same result of acceleration equals to negative w squared times x. Okay, so let's move on. Yeah, so like I was saying, you can use your sinusoidal graphs to describe the difference in displacement, velocity, and acceleration. And yeah, you can just draw it out. I think you know how to draw sine graphs. It's just just draw it nicely. Like, just be very clear on the translation and everything. Just use your skills on mathematics translation and then just draw your graphs nicely. Good. I don't think I need to explain this in great detail. I just draw the sine graph and then make sure the amplitude is equals to your x naught or v naught or whatever naught that you have. And then the period will help you determine the width of your so-called sinusoidal graph. So just be careful and then know when your graph, like, how to draw your graph. Okay, so so the next point is about kinetic and potential energy. Let me just drink some water. Okay, so in an object, the total energy will be equals to kinetic and potential energy, as we kind of saw last time, right? But in this scenario, we're not looking at stuff that's inside the atoms and all that, but more of the kinetic energy is derived from the speed of a big object and the potential energy depending on the height of the object or something like that. So if we were to look at the total energy, it'll be a constant line no matter what. Of course, you're assuming no energy loss, but in reality, a lot of heat energy keeps being transferred to the surroundings, so the total energy will decrease over time. But we'll look at that later. So if we assume that the total energy is constant all the time, then the kinetic and potential energy will just be interchanging with each other throughout the entire motion. So whenever kinetic energy increases, potential energy decreases, and likewise. So at the beginning, if it depends on where you start from. So you'll start from if you were to use the sine graph, we always start from the center, because in the sine graph it starts from zero, right? So that will be like the center of the motion. So if we start from the center, we know that at the center the velocity, if you look at the velocity graph, since velocity is like a cosine graph, imagine at t equals to 0 is actually maximum. So velocity is maximum at the center, and therefore your kinetic energy will be equals to the total energy at that point. And your potential energy will be 0 at that point of time. And since kinetic energy is a v squared graph, as we know that the velocity goes from maximum to 0 within the time that the pendulum goes from the center to amplitude. So kinetic energy is a v squared graph, so it will go from maximum to 0, and then once the thing goes back, it goes back to maximum velocity. But it won't go down, it'll go back up because it's a positive value. And the difference between the kinetic energy graph and the velocity graph is that the kinetic energy graph ends up having twice the frequency because it's completely positive. If you would be instead looking at the middle point as within that positive range. So when you do that, you end up getting a frequency that is twice the original frequency of the velocity graph. And that's the same logic for the potential energy graph. It will have twice the frequency. So I hope you understood why they have twice the frequency. It's not because they're different or something, but because of the way that we look at the graph. Okay, cool. So now we will look at the next point. Practical examples of damped oscillations. Oh look, real life, finally. We look at real life. We reference the effects of the degree of damping and importance of critical damping in applications such as a car suspension system. Okay, cool. Right, so in an ideal situation, you expect the oscillation to keep going on and on and on and on forever. But in reality, you don't really want certain things to be oscillating forever, right? So sometimes you try to dampen the oscillation using some kind of dampener or something that absorbs the energy, like it facilitates energy transfer. So if it's very light damping, it may decrease the energy a bit, but it will still be oscillating for quite some time. If it's very heavy damping, like very heavy, then what happens is that it's so damped that instead of just stopping, it tends to do a bit of weird random oscillation before actually stopping. It takes forever to get to equilibrium. So you need to give just the right amount of damping to stop the oscillations as quickly as you can. And that would be critical damping. So critical damping will be like just the right amount of damping to decrease the amplitudes really quickly and get it to equilibrium without any oscillation. And that's why they use it in things like car suspension systems, in which the wheel, like the like usually the tires have this dampener thing inside them. So when you're going over a bump, like a very rocky road or something, you don't want to feel too bumpy during your ride, right? So this will help to make it a little bit less bumpy and make yourself feel a little bit less nauseous at the end of the ride. So yeah, that's what it's useful for. But how do you get critical dampening? Well, you need to find the critical frequency, like you find the frequency at which, if you introduce a dampener that does the so-called frequent that sorry not critical frequency, no man, I don't know. You need to find the right frequency to set the dampener lah. If you do it at the exact opposite of the frequency that you're getting, you're basically cancelling it out. So I think that's how you do it. You do it at the frequency of the object, and then you make sure that it's opposite to the motion of the object, so that it will cancel out in a superposition or something. But I don't know, I'm not sure if that's correct. Anyway, that's not important, I hope. What's important is that you need to know how the graph looks when you draw the dampening, in a sense, and we'll look at that once we cover the other thing that we need to look at here. So now we look at forced oscillations. Oh, okay, forced oscillations. Okay, so for dampening oscillations, you're trying to get rid of the oscillations. When you're forcing an oscillation, you're trying to make something move at a particular frequency. So what you do is you have this system that drives the original object to oscillate. So this will be the driving frequency. So the driver will move at a particular frequency, and that's the driving frequency. And accordingly, your your object will start oscillating at a certain frequency, and that will depend on what exactly your driving frequency is. So for driving frequency, the best frequency that you can get to get the maximum possible amplitude out of the system is the natural frequency. So many systems have their own, each and every system has its own natural frequency. And luckily we have heat loss, because that prevents the amplitude from going to infinity. Like, because if you were to truly do natural frequency without any heat loss, as you see in those graphs that you get in your notes, might possibly get your infinite amplitude, and that will be disastrous. So yeah. Yeah. So in real life, when you build bridges and things like that, you definitely don't want people walking on it in the natural frequency of the bridge, because that's how the bridge can collapse. Like, sometimes the natural frequency can make the amplitude so high that the system cannot withstand it, like cannot withstand the forces of that, and it ends up breaking. Like, the structural integrity is, damaged from all of that oscillation. That's why it's pretty important to not oscillate it at that natural frequency unless you really need to. Okay, so if you were to draw this in a graph, basically you first draw the normal oscillation amplitude of the object, and as you go closer to natural frequency, it will go higher and higher, almost like it was infinity or something. So like, the natural frequency will be like a dotted line vertically, and then you draw the graph really high up, and then you go down again. Then for the dampening, dampening, you draw it at a lower amplitude, and you, based on the kind of dampening, you will get different responses of the amplitude. Yeah. So at critical damping it will be almost zero. Like it will go to zero very quickly. If it's not critical dampening, then it will be a different effect in the sense. Yeah. Okay, so now let's look at resonance. Resonance will be well, it's what you see in strings and in pipes. So those are two things that we'll be talking about. So resonance is when the when the object is oscillating at some kind of a natural frequency, and it's going at maximum amplitude, and it just goes between two different states, like up and down, up and down, up. Like really quickly it will be doing that. And in this scenario you have the entire system oscillating at exactly, like at a whole number of wavelengths, in a sense. Sorry, not wavelength, a whole number of, bumps. I don't know what to call that, like the crests, I suppose. Yeah. So how do you represent resonance? Well, in resonance we have, like, if you're looking at a string, it has various natural frequencies where the wavelength kind of corresponds in a fraction to the length of the string, in a sense. So if you were to look at the first harmonic frequency, like the first resonance point, you would see that the string is a complete dome, just like one big dome like that, and then it goes back down and up, down, up, down, up, down, up, down. So in resonance, your frequency, like your wave, isn't propagating anywhere. It's within the string. It doesn't go out or do anything. And that will also help us when we look at superposition. Sorry, wave motion in the sense. So it's actually a stationary wave. And in resonance, we in resonance we will look at it in terms of the frequency, speed, and wavelength. You know that the speed of a wave will be equals to frequency times the wavelength. So in this scenario, if you have a string with at the very first resonance, in the sense, you can then use your equation to to describe the speed or the frequency or whatever it is. So for the first one, this is actually like one wavelength is two of those crests, right? So just half a wavelength. So L is equals to half a wavelength, and from there you can, you know, yeah, you can do some equation. I think it's easier to write it down because I'm too lazy to tell everything out. So when L is equals to a wavelength, then you get a certain speed, frequency, blah blah blah, and so on and so forth. So usually it increases in terms of half a wavelength. So half 1 over 2, 2 over 2, 3 over 2, 4 over 2, so on and so forth. So L is equals to some n over 2 wavelengths. Then for the pipe, the pipe does have a little bit of extra gaps usually, like, which is called C. Like it's like a correction kind of thing. But usually you don't have to worry about that unless the question asks you about it. But so in normal circumstances, you would assume that there's no correction value in on the two ends of the pipe. So if the pipe is open on both ends, you can use the same thing as the string. If the pipe is closed, open end of the pipe, the node basically. Sorry, is it node? Sorry, nodes are the minimum points and antinodes are the maximum. Sorry. So the antinodes will be at the open ends of the pipe. So in this scenario, for the first one, it will actually only be 1/4 of a wavelength, and and then after it goes to 3/4 and 5/4 and 7/4 and so on and so forth. So I'll write down everything and hope to show you a table or something like that. I think that will be easier than me telling it out because I cannot really tell it out without getting confused. Yeah, so there are some places where resonance is useful and some places where it shouldn't be. We wouldn't really want it happening. So where is it useful? It's useful when you are trying to play musical instruments. You want your sound to sound nice. So you use resonance to get your string to vibrate at a certain frequency, and that gives you a particular note. And that's why they call out all of these harmonic frequencies because they're harmonious for some reason. So I don't know. And also in flutes, it's not the string instruments and the wind instruments. Uh, then where you should avoid it? Well, I guess the bridge. Yeah, like in places where you don't want the thing to be oscillating, you wouldn't want resonance either. Yeah, resonant oscillations are also useful in things like stereo equipment because they need to oscillate in order to make that noise. When you're playing your rock music or something, it uses some magnetic things to oscillate. Like the difference in magnetic attraction in a sense. That's pretty cool. So yeah, I think that's it. My voice is also tired. Yeah, so I hope you found this video useful. I think I talked for too long already. So yeah, if you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye!